Welcome. Okay, let's talk about related rates. I know, the name alone can sound a little intimidating, but if you've ever felt that calculus word problems are just abstract puzzles, today is going to change that. This is actually one of the coolest tools calculus gives us because it helps us describe a world that's always in motion. So let's dive right in. Just think about it for a second. A balloon is inflating. Its volume and its radius are both changing, and they're obviously connected. A ladder slips down a wall. Its height and its distance from the wall are linked. Or a person's shadow gets longer as they walk away from a streetlight. These things aren't just related, their rates of change are related. And that's the big question we're answering today. How do we figure out one of those rates if we already know another one? So, here's our game plan for today. We're going to start with the main idea and the secret role that time plays in all of this. Then I'm going to give you a 4-step master plan that you can use on pretty much any of these problems. We'll try it out on a balloon, a ladder, and a shadow problem, and then I'll get you ready to try it yourself. Okay, let's get right into it. What are we really talking about when we say related rates? At its heart, the idea is actually pretty simple. If two things, let's say two variables, are connected by an equation, then their rates of change, how fast they're changing, have to be connected too. And we use this awesome tool called implicit differentiation to find that connection. So if we know how fast a radius is growing, we can find out exactly how fast the volume is growing at that very same instant. Now, here it is. This is the part that trips up a lot of students, but I promise, once this clicks, everything else falls into place. The secret ingredient that connects all these changing variables is time. In all of these problems, you have to imagine that everything, distance x, volume v, radius r, is secretly changing over time. So when we take a derivative, we're always doing it with respect to time, which we call t. This means the rate of change for a variable like x is just written as dx over dt. That's the starting point for everything.
So what happens when you have something a little more complex, like r squared? Well, this is where the chain rule becomes your absolute best friend. The derivative isn't just 2r. No way. Because r is changing with time, we have to multiply by its own little inner derivative. So the derivative of r squared is actually 2r times dr dt. That dr dt on the end, that is the absolute key. It's the piece of the puzzle that links the rate of change of the radius right back into our equation.
Is this all feeling a little abstract? Don't even worry about it. The best part about related rates is that there's a repeatable, super reliable strategy to solve almost any problem they can throw at you. I like to call it the master plan. It's just 4 steps. That's it. First, draw a picture. I'm serious, don't ever skip this step. Label everything you know and what you're trying to find. Second, find an equation that connects all your variables. It's usually a geometry formula you already know. Third, you differentiate that whole equation with respect to time, t. And fourth, you just plug in all the numbers you have and solve for the one you don't. Let's see it in action. We're going to start with an absolute classic, the inflating balloon. It is the perfect way to see our 4-step plan just work its magic. So here's our setup. We're told the rate the radius is changing. That's our dr dt, and it's 2 centimeters per second. And what we want to find is the rate the volume is changing, dv dt, at the exact moment the radius, r, hits 10 centimeters. Okay, steps 1 and 2 of the master plan. We can picture the sphere, and we know our 2 variables are volume, v, and radius, r. The equation that connects them? That's just the formula for the volume of a sphere. This is our foundation. Easy enough. Now for step 3, the fun part, the calculus. We differentiate both sides with respect to time, t. So the derivative of v is just dv dt. On the right side, we use the power rule and the chain rule. The 3 comes down, cancels out the 3 on the bottom, and that leaves us with 4 pi r squared. But remember, r is a function of time, so we have to multiply by its own derivative, dr dt. See, there's that chain rule again, linking our rates together. And finally, the easy part, step 4. We just plug in the numbers we were given. We know the radius, r, is 10, and we know the rate of change of the radius, dr dt, is 2. We just substitute them right into that equation we just found. And we solve it. 10 squared is 100, times 4 is 400, times 2 is 800. So the volume is increasing at a rate of 800 pi cubic centimeters per second. And look at the units, centimeters cubed per second. That tells us we found a rate of change of volume, which is exactly what we wanted. Master plan complete. All right, that was a good warm-up, but does the master plan hold up when the problems get a little bit trickier? You bet it does. Let's level up and take a look at the famous ladder and shadow problems. So the classic ladder problem. Picture a 15-foot ladder leaning against a wall. Now, if the base is being pushed towards the wall, that means the distance x is getting smaller, right? So its rate, dx by dt, has to be a negative number. At the same time, the top of the ladder is sliding up the wall, so its rate, dy by dt, is going to be positive. This is a huge insight for these problems. The direction of the motion tells you the sign of the rate. So what's our equation? Well, it's a right triangle, so of course it's the Pythagorean theorem. X squared plus y squared equals 15 squared. Now for step 3, differentiate with respect to time. The derivative of x squared is 2x dx dt, and the derivative of y squared is 2y dy dt. The derivative of a constant, 15 squared, is just 0. After a little bit of algebra to solve for dy dt, we can plug everything in. And since our dx dt was negative, it cancels out the negative sign from the algebra, giving us that positive rate we expected. See, the plan holds up perfectly. Okay, now for a problem with a really cool twist. A person walks away from a streetlight, and their shadow stretches out. Here, the equation that connects everything isn't some simple geometry formula. We have to be a little clever and use similar triangles. We have the big triangle, formed by the light, the ground, and the shadow tip, and the little one, formed by the person's head, their feet, and the shadow tip. And this is where it gets, well, a little weird and totally counterintuitive. When you actually do the math here, you find out that the tip of the person's shadow is moving faster than the person is walking. How is that even possible? Let's check out the setup. By setting up a proportion, basically comparing the heights and bases of the two triangles, say the 12-foot lamppost over the 6.5-foot person, we get a really simple linear equation. And when we differentiate it, the rate of change of the shadow, dy over dt, is just a constant number times the person's speed, dx over dt. And this leads to an amazing conclusion. The shadow tip speed doesn't even depend on where the person is. It's always moving at a constant multiple of their speed, in this case about 1.8 times faster. So we've seen the plan work for spheres, for right triangles, and even for these tricky similar triangles with shadows. What's the big takeaway here? It's this. The master plan is your guide. It's your roadmap. The specific geometry might change, from a sphere to a triangle, but this 4-step process is your constant. Draw the picture, find the equation, differentiate with respect to time, and then solve. That framework, that is the key to cracking any of these problems. You've seen the theory, you've seen it in action, you get the critical role of time in the chain rule, and now you have a foolproof plan. The only thing left to do is to try it yourself. So, you've got the master plan. Are you ready to put it to the test?